Hello students, welcome to another beautiful lesson in Precalculus. So we're just going to be talking a little bit about matrices, just to clarify the most important things from this week's lesson. So let's see. So I have my handy dandy, why can't I see? I have my handy dandy, whiteboard here. So first, and the most key thing is for scalar multiplication. Excuse the beeping. My fire alarm battery needs to be changed. So with scalar multiplication, we think of scalar. Scalar is like the mathematical term for just a number. In relation to like vectors, matrices, and that sort. So scalar is really kind of like multiplying a number value times a matrix. So for example, let's take 5 times 3, 0, 1, negative 2. This scalar multiplication just means that we're multiplying every entry in our matrix here, and by the way, this is a 2 by 2 matrix, 2 rows and 2 columns. So we multiply every number in the matrix by the number 5. So we'll have 5 times 3, 15, 5 times 0 is 0, 5 times 1 is 5, and then 5 times negative 2 is negative 10. Okay, so our final answer will be the matrix here. Notice that it's still a 2 by 2 matrix, so scalar multiplication doesn't change the dimensions of the matrix. It only changes the value of the entries within the matrix. Okay. The second most important feature here in this unit is matrix by matrix multiplication. So there are a lot of different, what's the word I'm looking for? Restrictions, so to speak. So with scalar multiplication, 5, we have a whole number and it's positive, but we can multiply by a negative number, we can multiply by a fraction, by a decimal. There are really no limitations when it comes to scalar multiplication, or like any specific changes that happen. With matrix by matrix multiplication, on the other hand, there are some stipulations that you must abide by. So any matrix that you multiply, so using letters, let's say you have an A by B matrix, the only other type of matrix that you can multiply is one that has the same rows as columns. So this can be a B by A matrix. You can multiply these, or it can be some other term. But the most important thing is that whatever the number of rows is for the first matrix, it must match the number of columns in the second matrix. So this is the kind of restriction for matrix by matrix multiplication. So you have to make sure that you have the right dimensions before you multiply. So let's go through an example. So I'm going to give you the 2 by 2 matrix, 4, 2, negative 1, negative 1. And then I'm going to give you the 2 by 3 matrix. 3, 1, 0, 2, 1, negative 2. I just realized I said that incorrectly. Let me go back for a second. So I had the wrong thing. That's right. It's B times A or B times C. So I apologize for that. So the columns of the first row must match the rows of the second row. That's what it is, not the other way around. I apologize for that. It was a simple mistake. So it's actually the rows, the columns of the first matrix that you multiply must match the rows of the second matrix that you're going to multiply, not the other way around. So back to the matrices that we were looking at. So here we have a 2 by 2 matrix and a 2 by 3 matrix. And so the way I keep in track is that we're kind of going to squish these two dimensions together. And so what's going to happen is if we were to squeeze these together, these 2's in the middle are kind of going to go away, and we're going to be left with the 2 here and the 3 here. So it's going to be a 2 by 3 matrix when we finish multiplying. So it's kind of like a squeeze theorem, so to speak, when we think about why is it that we need the same number of columns for the first matrix and the same number of rows for the second matrix. So as you multiply two matrices, I like for you to circle the matrix, the row and column as you're going to work through it. So I always start by circling this first row here and then the first column in the second matrix. So as we write our solution here, I'm just going to have the brackets for the matrix. The first term in the row is going to get multiplied by the first term in the column. So 4 times 3 is 12. Then we're going to add the second term times the second term. So -1 times 2 is -2. So this is going to be our first entry in our new matrix that we're forming. Okay, so I'm not going to change my row. I'm going to keep this the same, but I'm going to move on to the next column. So 4 times 1 is 4, plus -1 times +1 is -1. I'm going to need a little more space. And then lastly, 4 times 0 is 0. -1 times -2 is +2 plus 2. Alright, now I can finally, once I've circled all the columns and done with those, now I can move on to the next row in the first matrix. So I have 2 times 2 and a -1, and I go back to the original or the first column in the second matrix. So 2 times 3 is 6, plus -1 times 2 is -2. Let's move on to the second. 2 times 1 is 2, plus -1 times +1 is -1. And then lastly, 2 times 0 is 0, plus -1 times -2 is a +2. So that's how we go about multiplying two matrices, and then we just finish off by adding together the entries that we just finished with. So 12 plus -2 is 10. 4 plus -1 is 3. 0 plus 2 is 2. 6 plus -2 is 4. 2 plus -1 is 1. And 0 plus 2 is 2. So this is our final matrix, and again it is a 2 row 3 column matrix, or 2 by 3. So these are the two key concepts from this particular lesson, because as we move on to our last topic on, as we finish out matrices and then move on to our last topic next week, just this concept is going to be important. And as you move on to further math classes, whether it's math applications or math SL or math analysis, then you're going to be needing to know how to do this multiplication with matrices, and you're going to have to recognize when to use it, how to use it, what restrictions there are, and so on. So just as a quick review, the first thing we talked about was scalar multiplication. That's simply multiplying some number or a scalar by a matrix, and this can be any type of number: positive, negative, fractions, whole numbers, decimals, it doesn't matter. And all it does is change the value of the entries within the matrix. It doesn't change the dimensions of the matrix at all. The second concept is matrix by matrix multiplication. So the two matrices must have the same columns for the first matrix as the number of rows for the second matrix. So those two things must be the same in order for you to be able to multiply the matrices. If that's not the case, then you cannot multiply them at all, okay? And so sometimes they'll give you trick questions about it, like giving you a matrix that doesn't match, and then you go through the work and you realize that it doesn't work out. So you have to be careful that you check that first, that the dimensions are going to match up, so that you know that, okay, if I do this work, I'm going to get an actual matrix, so that you're not wasting time. So the number of columns on the first matrix must match the number of rows on the second matrix. If not, you can't multiply them. If so, the matrix that you come up with must have the dimensions of kind of like the sandwich idea, where you smush them together, the twos go away, you're left with the 2 by 3, and then you multiply the entries in the first row by the entries in the first column and add up the two, and then just continue that pattern until you get your final matrix. Right? So it does change the dimensions of the matrix. Sometimes, as we see here, the matrix result will match one of the matrices you already have, but that may not always be the case. But the dimensions can change with matrix by matrix multiplication, while that doesn't happen with scalar multiplication.